Hello friends, welcome back to my YouTube channel. In this video, I will continue my discussion on the Ponchon-Savarit method. This will be 38th part of my discussion on distillation, and this will be the third video on the Ponchon-Savarit method. In the first, I introduced the method to you. In the second one, I discussed the theoretical background of this method, and today I'll be talking about the steps that are involved in this method. So at the end of this video, we will understand and learn how to use the Ponchon-Savarit method for finding number of plates in a tray comb. The Ponchon-Savarit method, it is going to give us the number of ideal stages that are needed to bring about the desired separation by fractionation. And what is fractionation? Fractionation is multi-stage distillation that is carried out in cylindrical tray columns. So as was the case with the McApthily method, which gives a number of ideal stages in a tray column, the Ponchon-Savarit method also gives the number of ideal stages or equilibrium stages or theoretical stages. So number of ideal stages required to bring about the desired separation by fractionation, which is multi-stage distillation carried out in cylindrical tray columns. Then once you get the number of ideal stages, you can easily find the number of real stages. For that, you need to use the overall tray efficiency. How is this overall tray efficiency given? Percentage overall tray efficiency is given by this formula, Ni upon Nr into 100. In this case, Ni is the number of ideal stages which we are going to get by using the Ponchon-Savarit method, and Nr is the number of real stages. So by using this equation, the efficiency will be known to us. We will be knowing the number of ideal stages that we get by using the Ponchon-Savarit method, and then you can easily get the number of real stages that are required to bring about the desired separation. So for getting the number of real stages, we need to know the overall tray efficiency, which is given by this equation. The number of real stages will always be greater than the number of ideal stages. That means the denominator will always be greater than the numerator. That's why percentage efficiency will always be less than 100. So we will know the steps that are involved in the Ponchon-Savarit method to get the number of ideal stages in a tray column. So for finding the number of ideal stages, typically what will be known to us, let us understand. First, we will know the following things about the feed. And we are, in our discussion, the feed will be a binary liquid solution of two components, A and B. And this A is the more volatile, that is boiling point of A is less than that of B, and its vapor pressure is higher than that of B. F and XF, these are known to us, that is molar flow rate of the feed and mole fraction of the more volatile component in the feed. They will be known to us. F is the molar flow rate of the feed, XF is the mole fraction of A in the feed. Then XD or XW or both may be known to us. What is XD? XD is mole fraction of A, that is mole fraction of the more volatile component in the distillate, and XW is mole fraction of A in the bottom product. Then D or W will be known to us, or both of them may be known to us. D is the molar flow rate of the distillate and W is the molar flow rate of the bottom product. Apart from this, reflux ratio will be known to us, and then enthalpy concentration data will be given to us, because as you know, in the Ponchon-Savarit method, we need to plot the enthalpy concentration diagram. And for plotting the enthalpy concentration diagram, enthalpy concentration data is required. So what is this? You will be knowing enthalpies of saturated liquids and corresponding mole fractions of A in those liquids. Then you will be knowing enthalpies of saturated vapor and corresponding and the mole fraction of A, that is more volatile component in those vapors. So HL, enthalpies of saturated liquid, will be known to us. Mole fractions of A in the liquid will be known to us or provided to us. Enthalpies of saturated vapors will be known to us, and mole fraction of A in those vapors, that will be known to us. Then the type of the feed will be given to us. That is very important. Unless and until you know the type of the feed, you will not be able to use the McApthilling or the Ponchon-Savarit method. Same is true for the McApthilling method. For finding number of stages by using the McApthilling method, type of feed is important. Type of feed should be known to us. So after knowing what information is available for doing the calculations, the next step would be calculation of unknown quantities. So the quantities involved in this case are F, XF, D, XT, W and XW. So F is the molar flow rate of the feed, it will be given to you. XF, mole fraction of the more volatile component in the feed, it will be given to you. And then out of the remaining 4, molar flow rate of the distillate, mole fraction of the more volatile component in the distillate, molar flow rate of the bottom product, and mole fraction of the more volatile component in the bottom product. Out of this 4, any one quantity may not be known to us, and we will have to find that quantity. Any one, at least any 1 or 2 quantities may not be known to us. Those will be unknown, and we will be finding those quantities in this step. So for that, we are going to use any unknown quantity from this list. Now the list will be D, because F and XF, they will always be known. So out of D, XD, W and XW, any unknown quantity or quantities, 1 or 2, out of this 4, they are to be calculated by using steady state total material balance. What is that? F is equal to D plus W. And along with this, steady state material balance for the more volatile component, that is in this case component A, in our case component A, that will also be required. So what is that? Fxf is equal to dxt plus w into xw. So you have 2 equations and there will be 2 unknowns. There are 2 equations and you can solve these 2 equations for 2 unknowns. So in that way you are going to get the unknown quantities. Then we also need to find Q1. What is Q1? You can refer my previous video on this. Q1 is the net heat removed at the top per mole of the top product. So it is given as, I write the formula, and how that Q will be used. Q will be used. How are you going to get Q1? You are going to get Q1 by using the equation for reflux ratio. What is that equation? R is equal to Q1 minus Hg1 divided by Hg1 minus Hd. So R is known, Hg1 and Hd will be known after you plot the enthalpy concentration diagram. And then the only unknown that is left is Q1, and you can get the value of Q1. Okay, so how Q1 is calculated? Q1 is calculated by using the equation for R. Now, my equation for R is this: Q1 minus Hg1 divided by Hg1 minus Hd. So you are going to get any 2 unknown quantities and then you are going to calculate Q1, the net heat removed at the top of the column per unit mole of the top product, that is distillate. Then after you have found out the unknown quantities and then Q1, you will be then plotting the enthalpy concentration diagram. So enthalpy concentration for that XY, that is mole fractions of the more volatile component in liquid and vapor phases, they will be plotted on x-axis, whereas on the y-axis we are going to plot enthalpies of saturated liquid and saturated vapor. At this end you have x is equal to 0, y is equal to 0, which represents pure B. I have talked about it in my previous videos, so please watch those videos. And this end will represent x is equal to 1, y is equal to 1. So the plot of enthalpies of saturated vapor versus mole fraction of the more volatile component in the vapor phase will give this curve, which is plot of y versus G, and we are going to get a lower curve, which is a result of plot of x, that is mole fraction of A in the liquid phase versus the enthalpies of saturated liquid. Then our task is we are supposed to locate the difference points, that is delta D. What are the coordinates of this point? XD and Q1. Then we are going to locate F, point F. And for locating point F, the coordinates of that point are known to us, XF and HF. Then delta W will be located. It will be having coordinates of XW and Q2. So first task is we will locate XD, and then we will locate XF, and then we will locate XW. We are going to locate these 3 points on the x-axis. Then after that we are going to draw vertical lines through those points. Vertical line through XD, and vertical line through XF, and vertical line through XW. Then knowing the value of Q1, we are going to locate it on the y-axis. And then from this we are going to go to the vertical line through XD to get a point, and this point is nothing but delta D. Then point F is to be located. So for example, I am assuming the feed to be saturated liquid. If the feed is saturated liquid, point F will be located on the lower curve. Again, depending on the type of the feed, the location of point F will change. The location will change along the vertical line through XF, that is fix. It will be lying on the vertical line through XF, but the location may change. So for saturated liquid, if the feed is saturated liquid, F will be located on the lower curve. So this is point F. So once point F you have located, earlier you located point delta D, then you simply draw a straight line through F to get this point. A point that intersects with the vertical line passing through XW, and that point is nothing but the y coordinate of that point will give you Q2, x coordinate is XW, so that means this point is delta W, which has coordinates of XW and Q2. So in this way, there's 3 points. It is important. The locating these 3 points is important in this method, in the Ponchon-Savarit method. So after plotting the enthalpy concentration diagram, next task is to plot the distribution diagram. So for that, mole fractions in the liquid phase, they will be plotted on the x-axis, that is small x will be plotted on the x-axis, and mole fractions in the vapor phase, they will be plotted on the y-axis, that is small y is plotted on the y-axis. So the diagonal line is drawn for the reference, and the actual plot will give us this curve, and this curve is the equilibrium curve. This curve is the equilibrium curve, actual plot. Whereas this is the diagonal line which is drawn for reference. Okay, so after plotting the enthalpy concentration diagram and then the distribution diagram. Next, let us know how to find the number of stages. We will be getting number of ideal stages. So let us know how to find those number of ideal stages. So for that, we will be using the enthalpy concentration diagram, which we have just plotted with all the points shown. At this end, you have x is equal to 0 and y is equal to 0. At this end, you have x is equal to 1 and y is equal to 1. And then you have delta W over here. So along with the enthalpy concentration diagram, we will also need the distribution diagram. To start with, we are going to locate this point. The point where the vertical line through XD intersects the upper curve. And I am going to read the x coordinate of this point. In this case, the x coordinate of this point is nothing but XD. And I am going to name this point as Y1. So, in the beginning, when you start, Y1 is equal to XD. So, with this Y1, we have to go to the distribution diagram, locate Y1 on the y-axis, then go to the equilibrium curve, and then come down to the x-axis and read the value of x. That will be corresponding x1. So, what is the significance of this? x1 is in equilibrium with y1. So, x1 and y1, they will be connected by a tie line on the enthalpy concentration diagram. So, after knowing x1, we are going to come back to the enthalpy concentration diagram and then we are going to locate x1, but we are going to do that on the lower curve. So, after you locate x1, you have two tasks. One is you will be drawing a line through x1 to x delta t. This is the construction line. First task. And then second task, you are going to connect x1 with y1 because they are equilibrium concentrations by a line. Here I have done that with the help of a dashed green line. This will be the tie line. The endpoints of this tie line are x1 and y1, which are in equilibrium with each other. So, after you do that, next task is to locate the point where construction line intersects the upper curve. That is this point. And I'm calling this point as y2 because I will be reading the x coordinate of this point on the x-axis. This is y2. So, I'm going to read this will be y2. So, with this y2, I will go back to the distribution diagram, then go to the equilibrium curve from y2 and get the corresponding x2. Then with this x2, I come back to the enthalpy concentration diagram and then I will locate x2. So, once x2 is located, again those two tasks. First, connect x2 with delta D and then connect x2, y2 with a tie line. In the process, you get this point where the construction line intersects the upper curve. Read the x coordinate of this point, let it be y3. With this y3, come back to the distribution diagram, go to the equilibrium curve, get the corresponding x3. With this x3, come back to the distribution diagram, enthalpy concentration diagram and locate x3 on the lower curve. So, while locating x3, you must have noticed that we have crossed the line that passes through F, delta W and delta T. So, once x3 is located and now x3 is on the left side of this line, the line that passes through F, now the construction line will not go to delta D, it will come to delta W. So, the construction line will be drawn like this through x3 to delta W and then you will extend it to the upper curve to get this point because you are going to read before that x3 and y3 they will be connected by a tie line and then you are going to read the x coordinate of this point. Let this be y4. Then with y4 we will come back to the distribution diagram, get the corresponding x4. Take that x4 to the enthalpy concentration diagram, locate it, then draw the construction line through x4 from delta W, and then connect X4, Y4 with a tie line. You get this point. Call this as the X coordinate of this point is Y5. Take this value of Y5, go to the distribution diagram, get the corresponding value of X5, take this value of X5, come back to the enthalpy concentration diagram, locate it, then draw the construction X5 that goes to delta W and intersects the upper curve. So you are drawing the construction line. In that process, you get this point. You read the X coordinate of this point. That will be Y6. Before that, you have to connect X5, Y5 with a tie line. Then you get Y6. Read Y6, get the value of Y6, go to the distribution diagram and get the corresponding value of X6. Then come back to the enthalpy concentration diagram and locate X6. Once you locate X6, you must have noticed that we have crossed the vertical line through XW. So once you do that, when you cross the vertical line through XW, you have to stop. So now you'll draw the construction line through X6. That will be the last construction line for this particular case. And then you are going to connect X6 with Y6. So we now have to stop because we have crossed the vertical line through XW. Now the task left is you have to count the tie lines, the green dash lines in this case. Those tie lines, let us count this as number 1, 2, 3, 4, 5 and 6. So in this particular example, there are 6 stages. Number of tie lines is equal to number of ideal stages. And one out of those ideal stages will be the reboiler. So for this particular example, number of ideal stages, if I denote it by Ni, these are 6. But out of that, those 6, 5 will be the stages and 5 will be the stages and 1 will be the reboiler. So in this way, you have to find the number of stages by this Ponchon-Savarit method. You have to use both the diagrams, the enthalpy concentration diagram and also the distribution diagram. So you have to move from enthalpy concentration to distribution and from distribution to enthalpy concentration. You have to draw the construction lines. You have to draw the tie lines. Remember, tie lines will be connecting equilibrium concentrations. For example, you check any, let us say 5th tie line. It is connecting X5 and Y5. X5 and Y5, they are in equilibrium with each other. So X3, Y3. X3, Y3, they are in equilibrium with each other. So actually you are calculating the tie, you are counting the tie lines. And those tie lines are nothing but ideal stages in this particular case. So in this way, you have to find the number of ideal stages. So I hope now you know how to construct those stages by this method. You just understand the steps. If you have any doubt, you please come back to me with your comments. I will help you. Then another task is how to get the minimum number of stages. So for that, what is the concept of minimum number of stages? You already know. When the column is operating under total reflux. So I am quickly showing the column over here. So enough feed is given to the column and then feed closed down and then feed is stopped. The liquid feed is taken to the free boiler. It is boiled by supplying heat. The resulting vapors, they are sent into the column. Those vapors will be rising. They will be taken out from the top. They will be cooled in the condenser to get the condensate, and all of the condensate will be written back to the column as reflux. So all condensate is written as reflux. No distillate is taken out. So this is how you can represent a column that is operating under total reflux. then the reflux after entering the column, it will be flowing down and then it will join the liquid part. So F is 0 when the column is operating under total reflux, D is 0 when the column is operating under total reflux, W is 0 when the column is operating under total reflux. So no distillate is taken out. A reflux ratio is infinite because D is 0 and reflux ratio is nothing but ratio of reflux stream to the distillate stream. So if this is 0, this will be infinite. You know this. I have discussed this many times. So reflux ratio is infinite. No bottom product is taken out. I have a separate video on distillation under total reflux on my channel. You please watch that. So no bottom product is taken out. Required number of stages are minimum. And now we are going to know how to find those minimum number of stages. And condenser and reboiler duty, E duties are maximum. Why those are maximum? Again, please watch the video. Watch my video on distillation under total reflux. You'll get answer to this question. Q1 is given by this equation. We know QC plus D into SD by D. So when D is 0, that means Q1 will be infinite. Q1 is infinity. The Q2 again, which is given as WHW minus QR upon W, W is 0. That means WHW minus QR upon 0 is infinity. So in this case, both Q1 and Q2 are infinite when the column is operating under total reflux. So the meaning is, one of the coordinate of what is Q1, if you remember, Q1 is one of the coordinates of the point delta D, XD and Q1. So if Q1 is infinity, that means it will be located at an infinite distance. And delta W, it has coordinates of XW and Q2. So again, Q2 will be located at an infinite distance. That's why I'm saying on the enthalpy concentration diagram, delta D with coordinates XD Q1 and delta W with coordinates XW Q2, they are located at infinite distance, at infinity. And this is the concept that we will be using to find the minimum number of stages, which happens when the column is operating under total reflux. So how to get the minimum number of stages? Let us understand. So you have this enthalpy concentration diagram. So the reflux ratio is given by this formula. R is equal to Q1 minus Hg1 upon Hg1 of minus Hd. So if you increase the reflux ratio, what is going to happen? Delta D moves upwards because Q1 is going to increase. So delta D is going to move upwards, and at the same time delta W is going to move downwards. So with increase in reflux ratio, delta D is going to move upwards, delta W is going to move downwards. And if you make the reflux ratio infinite, which is possible when the column is operating under total reflux, then delta D will be located at an infinite distance. Delta D is located at infinity and delta W is also located at infinity. So that is the concept. So when reflux ratio is infinite, that is when the column, which is true when the column is operating under total reflux. Okay, so let us learn how to get. So you have the enthalpy concentration diagram. I'm quickly drawing the diagram. X is equal to 0, Y is equal to 0, X is equal to 1, Y is equal to 1. The upper curve, the lower curve. We locate XD, we locate XF, we locate XW. We draw vertical lines through those 3 points. And then you locate F. We need the distribution diagram. then there is no need of locating Q1 because it will be located, or it is located, in this case it is located at an infinite distance. So there is no need of locating Q1. And there is also no need of locating delta the Q, because Q2 is infinity. Delta D, it will be located at an infinite distance. Delta W, it will be located at an infinite distance. So you just have to draw. So again, start with Y1, locate this Y1, go to the equilibrium curve, find out corresponding X1, locate that X1 on this. Now the two tasks in this case, when you are going to find the minimum number of stages, you just have to draw a vertical line through X1. That will be the construction line, because vertically it will be going to an infinite location where Q1 will be present. So you just have to draw a vertical line. That will be the construction line in this case. Then you connect X1, Y1 by the tie line. Then read this point as Y2. Read this point as Y2. Come back to the distribution diagram. Get the corresponding X2. Locate X2. Draw a vertical line through X2. Connect X2, Y2. Read this point Y3. Go to the distribution diagram. Find the corresponding X3. Come back to the enthalpy concentration diagram. Locate X3 over here and draw the vertical line. Again, there is no question since we are crossing F. There is no line through F, delta D and delta W, because it will be vertical line, because both delta D and delta W, they are located at an infinite distance. So that's why again you just have to draw a vertical line through X3. So connect X3, Y3, locate Y4, find out corresponding X4, locate X4 on the enthalpy concentration diagram, draw the vertical line, connect X4, Y4, locate Y5, come back to the distribution diagram, get the corresponding X5, locate X5, and in that process we have crossed the vertical line through XW. That means we have to stop after drawing the construction line, connect X5, Y5. So that ends. So in this way, the number of tie lines you have drawn will be the minimum number of stages, minimum number of ideal stages. So if I count, this is 1, this is 2, this is 3, this is 4, and this is 5. So in this case, minimum number of ideal stages is equal to 4 stages plus 1 reboiler. So this is how you have to use the Ponchon-Savarit method, that is the enthalpy concentration diagram, to find the minimum number of stages in a typical 3-column. Okay, so after knowing how to find the minimum number of stages, now let us learn how to find the minimum reflux ratio. What is the concept? I have made a separate video on the minimum reflux ratio. You can watch that. But at the minimum reflux ratio, what happens? The operating lines for the rectifying section and stripping section on the distribution diagram, they intersect with each other on the equilibrium curve. So I have discussed how this happens in my video on the minimum reflux ratio. So over here, you understand, when you are using minimum reflux ratio, then the operating lines for the rectifying and stripping sections, the operating lines that we draw on the distribution diagram, they will intersect on the equilibrium curve. So I will show how that happens. So this is the distribution diagram, and you can see when the column is operating under minimum reflux ratio, or when you are using minimum reflux ratio, then the operating lines, this is the operating line for the rectifying section, this is the operating line for the stripping section, this is the Q line, and now all the three lines, they are intersecting on the equilibrium curve. So this concept we have understood, or I have discussed in my discussion on the McCabe method, how this works. So you can refer that. So this is the rectifying section line. This is the stripping section line, and this is feed line, or we call Q line. And now they are intersecting on the equilibrium curve. So when these lines, they are intersecting on the equilibrium curve, the driving force for mass transfer becomes zero, because the driving force is the magnitude of the distance between the equilibrium curve and the operating line. Now when they are intersecting on the equilibrium curve, the distance becomes zero. We are talking about distance along the Q line. So when they are intersecting on the equilibrium curve, the distance becomes zero. And since the distance is zero, the driving force for the mass transfer, it also becomes zero. And therefore, in such situation, we will need an infinite number of stages to bring about the desired separation. The desired separation will be possible only when you will need an infinite number of stages in the operation. And to accommodate those infinite number of stages, an infinitely tall tower will be required. So minimum, but the only benefit that you can have with minimum reflux ratio is heat duties for the condenser and the reboiler, they will be minimal. Because with minimum reflux ratio, minimum amount of liquid will have to be boiled in the reboiler, and minimum amount of vapor will have to be condensed in the condenser. That's why when you are using minimum reflux ratio, the heat duties for the condenser and the reboiler, they are minimal. So I have already discussed this. This is just, I am just summarizing those points. What happens when you are using minimum reflux ratio. Now our objective in this discussion is, let us learn how to find minimum reflux ratio by using the Ponchon-Savarit method. Okay, now let us know how to get the minimum reflux ratio by using the Ponchon-Savarit method. So for that we will be using the enthalpy concentration diagram. This end is x is equal to 0, y is equal to 0. This end is x is equal to 1, y is equal to 1. And all other points, you know, I have just discussed all those, how those points are located on the enthalpy concentration diagram. Now, the reflux ratio we know is given by this equation. R is equal to Q1 minus Hg1 divided by Hg1 minus Hd, where Q1 is the y coordinate of the point delta D. Hg1 is the y coordinate of this point. So you just have to read Hg1 as the y coordinate of this point, and Hd is the y coordinate of this point, Hd, y coordinate of this point. So you can read Hg1 and Hd1, or you can get Hg1 and Hd from these 2 points. I hope this is clear to you. So for you have this point, you go to the y-axis, read the value of enthalpy, that will be Hg1. Then for this point, you go to the y-axis, read the y coordinate, that will be Hd. And then you can use those values to get the reflux ratio. Now, if we are decreasing the reflux ratio, when the column is operating under total reflux, the reflux ratio is infinite. Now, if the reflux ratio is decreased, what happens on the enthalpy concentration diagram? Let us understand. The point delta D, this point, it moves downwards along the vertical line, along this vertical line that we have drawn through xt. and at the same time the point delta W, it moves upwards along the vertical line that is drawn through XW. So with decrease in R, this happens. Delta D moves downwards and delta W, it moves upwards. And we know how the stages are drawn, the tie lines are drawn. So for example, I have, for your understanding, I am showing this blue line is the construction line and this dashed green line is the tie line, which is nothing but the equilibrium stage. Now, let us understand what happens to these lines as this delta D moves downwards, which is happening when you are decreasing the reflux ratio. So, as delta D moves downwards, tie lines and construction lines that we draw to this point delta D, they move closer to each other. So, if when you go on decreasing R, delta D will be moving downwards, and as it moves downwards, what is happening? Tie lines and the construction lines, that is the tie line and the construction lines, they move closer to each other. So this is the effect of decrease in reflux ratio. Decrease in the reflux ratio. The construction line, I hope it is visible to you, the blue line that I have drawn, it moves closer to the equilibrium, the tie line. So, as the process of decreasing the reflux ratio is continued, you will reach a situation where tie lines and the construction lines to the point delta D, they will coincide with each other. So, we just understood, if you are decreasing the reflux ratio, the construction lines and the tie line, they are moving closer to each other. And in the process of decreasing the reflux ratio, you will reach a situation when this tie line will coincide with the construction line. And when this happens, there will be one tie line, one such tie line which is coinciding with the construction line that has highest location for delta D and delta that will have highest location for delta D, and that location we are going to identify by the point delta D young. So as the reflux ratio is decreased, the construction lines and tie lines, they are going to come closer to each other. A situation will reach where the construction lines and tie lines will coincide with each other, and there will be one tie line which will give highest location for the point delta D. Highest location, but that is below the point delta D. So delta D is moving downwards, and you will reach a situation when the construction line will coincide with the tie line, and one of the tie line will be giving highest location for the point delta D, and that location will be identified by the point delta DM. At the same time, this tie line will give the lowest location for the point delta W, and that location will be delta WM, or that location will be identified by delta WM. So this tie line, the tie line which does these things, the tie line that gives highest location. Now, the tie line that we are talking about, first is it coincides with the construction line, then it gives highest location for delta D at delta DM, and at the same time it gives lowest location for delta W at delta WM. The same tie line, it passes through the point F, that we have on the concentration diagram. This tie line which gives highest location for delta D and lowest location for delta W, and plus it coincides with the construction line. This tie line passes through F, the point F on the enthalpy concentration diagram, the point F that you are now. Okay, now let us know how those points delta Dm and delta Wm, they are located on the enthalpy concentration diagram. So for that, I am showing you the enthalpy concentration diagram once again. This is x is equal to 0, y is equal to 0, x is equal to 1, y is equal to 1. And we will need the distribution diagram as well. So I am taking that also in our discussion. Okay. Now we are concerned with the tie line that passes through F. You please remember, based on the previous discussion where we talked about the tie line that will give you highest location for delta D and lowest location for delta W. That tie line will be passing through point F, I told you. So such a tie line that passes through point F, if you could draw and extend the tie line to the vertical lines through XD and then XW, we will be getting delta Dm and delta Wm. So for that, we need to draw a tie line that passes through XF, or we need to draw a tie line whose one end or whose end on the lower curve is at point F. What is the x coordinate of point F? It is XF. So we are concerned with that concentration in vapor phase that is in equilibrium with XF. So once you know that concentration, you can locate it on the upper curve and then you can draw a tie line. That tie line will be passing through point F. So right now you just understand, in order to draw a tie line through F, we need to know the concentration in vapor phase that is in equilibrium with XF. And how are you going to get that? You can get that by using the distribution diagram. So you have to locate XF, then you go to the equilibrium curve and then move on to the y-axis, and here you will read YF. So this YF is in equilibrium with XF, and on the enthalpy concentration diagram, XF and YF will be connected by a tie line, and this tie line is passing through the point F. And then we are going to extend that tie line so that it meets the vertical line through XD and vertical line through XW. And then you will be able to locate delta Dm and delta Wm. Okay, so once I read YF on the distribution diagram, I will locate it over here. So this is YF. Now this is XF. So you just, this is XF means the X over here you have XF. Now I'll be drawing a tie line that passes through this point and this point. So if I do that, I draw a tie line like this. So when I'm doing it, I get this point. So this point will be delta Dm. I get this point will be delta Wm. So this tie line is giving highest location for delta D. If you have the case where tie line coincides with the construction line. So this will be the highest location. All other tie lines will be intersecting below this point. All other tie lines. Only one tie line that passes through F will be giving the highest location. We are talking about location below the actual delta D point. So all other tie lines will be intersecting below this point. And same is the case with this. All other tie lines will be intersecting the vertical line below above this point. So this will be the lowest location. So this point is delta Dm, and let us read the y coordinate of this point as q1 dash, because we are going to use that in finding the minimum reflux ratio. And let us read the y coordinate of this. This will be delta Wm, and the y coordinate for this is q2 dash. So in this way, delta Dm, this will correspond to minimum reflux ratio. So in the formula for reflux ratio, if you replace q1 with q1 dash, the resulting reflux ratio will be the minimum reflux ratio. I hope the concept is clear to you. If you have any doubts, you please mention those doubts in the comment section. So this is a tie line which we have obtained after decreasing the reflux ratio and reaching a situation where it is coinciding with the construction line. And when this happens, then you get this point. Now the tie line and construction line, they are coinciding with each other. And we are getting delta Dm and delta W here. So the difference point for R minimum, that is minimum reflux ratio, is delta Dm. What are the coordinates of this point? XD and Q1 dash. And delta Wm will have coordinates of XW and Q2 dash. Then the minimum reflux ratio will be given by this formula. The formula remains the same. The only change is you are replacing Q1 with Q1 dash. So in this way, you can find minimum reflux ratio by the Ponchon-Savarit method, or by using the enthalpy concentration diagram. I hope you have learned how those points delta Dm and delta Wm are located. Again, I'm telling, if you have any doubts, you please mention those doubts in the comment section. I will surely answer your questions. So with this, I end my discussion on the steps involved in the Ponchon-Savarit method. So we have discussed steps for finding the number of equilibrium stages. Then we have learned how to find the minimum number of stages, and we have also learned how to find the minimum reflux ratio. I hope the concept is clear to you. Now you know the steps, and in my next video on the Ponchon-Savarit method, I will be solving a numerical where we will find number of stages, number of equilibrium stages, we will find number of minimum stages, we will find the minimum reflux ratio. Along with this, we will also learn how to find the heat load on condenser and the reboiler. For this video, thanks for watching the video. Do subscribe to my channel. Tell your friends to subscribe to my channel, because fundamental concepts of chemical engineering, and over here fundamental concepts about distillation, are discussed on my YouTube channel. So I hope you'll subscribe to my channel. Tell your friends to subscribe to it. And I'm sure you'll join me in my next video. Well, I'll be discussing a numerical based on the Ponchon-Savarit method. For now, have a nice day. Bye-bye.